Lab 2, Motion of a Falling Object. The purpose of this lab was to observe an object in falling motion from rest, as well as studying the effect of drag on an object in freefall in terms of acceleration and gravitational acceleration. The experiment observed a cowboy hat free falling from rest. It also involved two computational models, one with drag applied and one with only conserved acceleration from gravity, both consisting of Newton's second law of motion and its postulates, as well as the drag force equation. Newton's second law of motion and the drag force equation. Newton's second postulate of his law of motion states the change in momentum divided by the change in time or rate of change of momentum is equal to the net force enacted on said object in observation. This deduction becomes incredibly useful for classical physical observation, as momentum is made up of velocity and mass of the object. The drag equation was also used for finding the drag force holding density and surface area constant, as there's no viable means to calculate this for the cowboy hat at this level of experimentation. And why to use them. For Newton's second law, with some variable manipulation, final momentum and final position, and much more, can be determined. With a constant velocity and mass, this experiment becomes a perfect example of an observed object in motion that can be modeled easily with the momentum and position update formulas. With both of these equations, GlowScript can accurately model the updated position of our observed object every 0.05 seconds for the change in time, or delta t. Systems and surroundings. For the observed experiment, the system itself under study is the cowboy hat in freefall. The surroundings are everything else, including air, gravity, and drag on the hat. This is the tracker video. Mass and diameter of the cowboy hat, as well as looked at the drag coefficient of the cowboy hat. The hat started from rest, so the only applied forces were gravity and drag. The mass of the hat was 0.17 kilograms, the diameter was 0.0254 meters, and the initial position was 000 meters as it started at the origin within tracker, and the initial velocity was 000 meters per second as it was at rest. The drag coefficient from the internet stated for the cowboy hat was 0.65. These were the position curves for empirical data, as well as both of the computational models. The red model was that without drag, and then the blue model was the computational model with drag applied. The tracker data is highlighted in yellow. The computational model components. The most important components of the computational model started first with the initialized mass of 0.17 kilograms of the hat in line 36. The initial position 0 meters and velocity 0 meters per second were then entered in lines 38 and 39. Initial time 0 seconds, as well as the change in time step 0.05 seconds, were initialized in 41 and 42. The model then truly computes the motion with the while loop from t equals 0 to t equals 0.95 seconds in lines 55 to end. The drag formula is applied for the net force in 62 and 63. In line 67, the velocity update formula, and line 69, the position update formula, both derived from Newton's second law, are computed every 0.05 seconds. The position curve of the hat given by the tracker data is slightly off from the drag applied computational model. This is due to the tracker data following the actual position of the hat versus the computational model modeling constant acceleration and perfect resistance. This is also likely different due to the human error and the frame rate of the video, which, despite being manipulated, still lagged. Sources of error. Some possible sources for the difference between our computational model include the shape of the hat and the fact the found drag coefficient was for a general cowboy hat, while they observed was a cheap, lightweight one. Furthermore, the hat also changes path due to air resistance, thus some X component that is there that's not measured in the lab, decreasing the velocity in the negative Y direction. Finally, the video had to be reshot 4 times, as even adjusting the frame rate to the correct interval for tracker kept adjusting the frames, distorting the video. Discussion. The lab ultimately exemplified Newton's second law of motion and the drag force equation by observing an object's motion in free fall with gravitational acceleration and drag force applied. The cowboy hat falls with gravity and drag interacting for a net force that eventually becomes balanced in equilibrium for terminal velocity. This terminal velocity is exemplified by the velocity curve modeled in the drag applied computational model to the right, where the curve levels out after accelerating over time. Which, if any, of your models, if your model predicts terminal velocity? The drag applied model predicts terminal velocity. This is due to the model calculating the drag force applied to the cowboy hat. When this force becomes balanced with the force of gravity, the hat stops accelerating and a constant terminal velocity is observed. If it was thrown downwards with an initial velocity, would the terminal velocity in this case be the same or different from the case where it was dropped from rest? The drag coefficient is always the same, and the drag force and gravity will become balanced for a new net force. But the initial velocity added would change the effect of terminal velocity. When applied to the computational model with drag, the hat reaches a terminal velocity different from the initial model. In real life, though, air resistance would cause the hat to decrease in velocity to the same terminal velocity once again.